Good afternoon, everyone. In this series of video, I wanted to talk about the most three important principle in mathematics. And actually, some of you already seen this principle before or heard of it. One of them is called mathematical induction. And if you already taken pre-calculus, that's the first time you introduced to mathematical induction. But you don't really know why we can use that principle. So today, I want to talk about how we can come up with mathematical induction. Okay. Then we can we talk about the proof of mathematical induction. And we also learn about the second mathematical induction, that's the second principle. And the first principle we call the well-ordering principle. Those three principles are related to each other. What I mean is that from well-ordering principle, we can derive the first principle of mathematical induction. And from the first mathematical induction, we can derive the second mathematical induction. So those three principles over there I'm talking about right now are equivalent to each other. So in this series of video, I want to give you the proof, okay, of first mathematical induction. So if I have time in the second video, I'm going to talk about the second proof of the second mathematical induction. But before I doing the proof, I want to talk about the well-ordering principle. So the first part of the video today, I want to talk about well-ordering principle. Okay. What is well-ordering principle? Well, let's get back to when the first time you learn mathematics, you learn integer, right? And you introduce to negative integer and positive integer. So all integer is we're gonna put in the set we call the set of integer, right? And the set of integer is notated as a z, like this. This is called a set of integer. Okay. But today I want to just talk about the set of non-negative integer, or we can call the set of positive integer. So the set of non-negative integer, we notate it as a z with a plus sign. This is a set of positive integer. Okay. Why I have to review this? Because in well-ordering principle, it's related to the set of positive integer. And this principle states that for every non-empty subset of a set of the set of positive integer, okay, there always exists the smallest element. Okay, the smallest element. What I mean over here is that the principle means that if you pick a subset of non-negative integer, okay, a subset of non-negative integer, or the subset of a positive integer, okay, there always exists the smallest element in that set. That's what it means. Okay. And from this principle, I can come up with a set. We call it a set Z sub m. What is the set Z sub m? Z sub m is a set of positive integer, okay, that is greater than or equal to m. Okay. Okay. And we can write the set Z sub m as follows. For an m integer, okay, let me add this. M is integer. Z sub m is equal to, this is a set, okay, of the x, the set that contains all the integer x, and x is a member of positive integer, okay, and x must be greater than or equal to m. Okay. You know, I know some of you are already familiar to a set builder notation. So this is like a set builder notation that we use the curve bracket. Okay. Then of course this set over here is well ordered. It's well ordered. Yes, because it's contained in this set. It's all positive integer, and this set contains a number m, and this number m over here is the smallest number in this set. Okay, so I can say that Z sub m is well ordered. Okay. From this principle, I can come up with a theorem, and this theorem we can use to prove the first principle of mathematical induction. And the theorem said that let S be a subset, let S be a subset of Z sub m, okay, with property, okay, the first property then, m belong to S. Okay, it means that S contain a member, and the member here is I call it m. Okay. The second property is if X also belong to S, S also contain another member we call the X, and this implies X plus 1 also belong to S. Then we can conclude the set S over here, the subset S over here is equal to Z sub M. Okay, equal to Z sub M. So how are we going to prove this? This proof is very important. By understanding this proof, you can prove the first mathematical induction. Okay. So how are we going to prove it? We, if some of you already taken logic and proof course, right? You guys have been introduced to several methods of proving. Okay. We can use mathematical induction to prove. We can use the direct proof. We can use contradiction proof, right? We prove by contradiction, or we can prove by using the contrapositive logic. Okay. So in this theorem, I want to use contradiction method. So we're gonna prove this by contradiction. Okay. So we're gonna start from the conclusion right here. Okay. Over here, they want us to prove that S equal to Z sub M. So I'm gonna assume because we prove by contradiction. So I'm gonna assume that S is different from Z sub M. Okay. So we start with this, right? We start with this, and we're gonna go backward. We're gonna have a logic some way somehow, so that at the end it gives us a, a statement that doesn't make sense, a statement that contradicts to the I can say that it contradicts to the I'm gonna say that let me see. So we assume this statement, and some way somehow this statement will lead to a contradiction. It will lead to a validity of the truth. Okay. So how we're gonna do this? So if S is different from Z sub M, if S is different from Z sub M, and S over here, S is a subset of Z sub M. Okay. S is a subset of Z sub M. What can we obtain if we suppose that S is a subset of Z sub M and S is different from Z sub M? So this is imply what? Okay. Imply that there exists another non-empty set. Okay. Say S prime, for example. Okay. And this S prime here, okay, also a subset of Z sub M. And because it's also a subset of Z sub M, so it contains some element of Z sub M, right? So says so S containing element, not all of them, but just some element of Z sub M. Okay, contains some element of Z sub M. And this element here, okay, this element here does not belong to S. Contains some element of M, which does not belong to S. Well, if I draw the picture for you, you can see right away. What if I have something like this? I have Z sub M like this. Okay, this is Z sub M. Okay. And I say that S is a subset of Z sub M. Okay, S is a subset of M. Then there exists another non-empty set, say S prime. And because S is different from Z sub M already, okay, S is different from Z sub M, and S is a subset of Z sub M. So S will be right here. Okay, this is your S. Right? Because we say that S is a subset of Z sub M, right? And S is not equal to Z sub M, so S will be inside Z sub M. Okay. Then of course there's another set here, right? There's another set here. Could be any set, right? I call the S prime here. And you see the S prime here, okay? I'm sorry. You see the S prime over here, okay? It's also the subset of Z sub M, right? And it contains some element here. And this element here, it belongs to Z sub M, right? But it does not belong to S. Okay? I can say we can say that element is K, for example. We can say that element is K. So this is element K. Okay. And this element K over here, I can say that K is the smallest set, because according to well ordering principle. Okay, so we say that S, we know that S prime is a subset of Z sub M, right? And because S prime is not an empty set, okay, and that's why. So by well ordering principle, S prime has a smallest as the smaller element, say K. Okay, so K over here is the smallest element. Okay, what next? All right, and we over here, they give us that M belong to S, so M is will be over here. M will be here, right? M belong to S. Okay. And K, it belong to S prime. So M is different from K. Right? Well, it doesn't make sense, right? It doesn't make sense because totally makes sense, because if M belong to S and K belong to S, okay, K belong to S prime here, okay, then of course M is different from K. M is different from K, and because M is the smallest number of Z sub M, you see that M is the smallest number of Z sub M, so K must be greater than M, greater than equal M. Well, greater than M, because M is the smallest number already. So K must be greater than M. Okay. All right. That totally makes sense, you know. Let's see what next. What is the next logic here? So we have K greater than M. K greater than M. So and K is the smallest element in S prime. Okay, K is the smallest element in S prime. So what? K minus 1 is also greater than it. It's also greater than it. Because look at that, M is the smallest element in Z sub M already. So K minus 1 must be greater than M, right? It cannot be smaller than M. It must be greater than or equal to M. Okay. So K minus 1, it follows that. It follow what? So K minus 1 is greater than or equal to M, and K is the smallest. Okay, K is the smallest of S prime. So it follows that K minus 1, okay, must be belongs to Z sub M. Okay, and K minus 1 cannot be in S prime. Why? How come? K minus, we know that K minus 1 is less than K. Okay, and K is the smallest in S prime already. Then K minus 1 cannot be smaller than K. You know, if it's smaller than K, then K minus 1 is the smallest one. Okay, so k minus 1 over here cannot be in S prime. And because it cannot be in S prime and k minus 1 is in Z sub m, so k minus 1 must be in S. Right? It totally makes sense. It totally makes sense. Okay? So k minus 1 in S. So what would we have? We have k minus 1 in S. So we can state that, let's see how we go from here. We have k minus 1 belong to S. Okay. Minus 1 belong to S. Let's see how I'm gonna use this, because this is the this is what they give us, so we can use this. So k minus 1 belong to S, right? Just think about it. K minus 1 belong to S. Okay. They give us what? They give X belong to S. X plus 1 also belong to S. So if k minus 1 belong to S, so k minus 1 plus 1, right, also belong to S. Okay, k minus 1 plus 1 also belong to S. And k minus 1 plus 1 is the same as, is it in other word, k belongs to S. Minus plus cancel. So k minus 1 plus 1 belongs to S. It means k belongs to S. Okay. And k belongs to S, but at the beginning we say what? We say that k here belong to S prime. Oh, so you see that there's a big contradiction over there. Okay, it contradicts to the validity. Okay, contradict to validity here, because how come k belong to S prime and k belong to S at the same time? No way. Okay, so k belong to S and k belong to S prime. This is lead to a contradiction, because it doesn't make sense. Okay, this is false. This is false because it's not true, but it leads to something that untrue. Okay, that leads to something that untrue, because how come k belong to S and k belong to S prime at the same time? Okay, and because this is contradiction, so what we assume over here is wrong. Okay, so what we assume over here is wrong, and because it's wrong, finally we can conclude that S must be equal to Z sub n. Okay, everybody understand this, right? This is false. This is false. So this step, what we assume over here is also false. This step, what we have over here, that leads to something invalid. Something is not true. Something is not correct, right? Because how come k belong to S and k belong to S prime at the same time? There's no way. Okay. So this is the proof of the theorem. The first theorem here. This theorem I'm going to use to prove the first principle of mathematical induction. But we need to know what mathematical induction is, right? So what is mathematical induction? Second part. And in this part, I want to talk about first principle of mathematical induction. Okay. Mathematical induction is like a domino effect. Where a domino effect. I don't know. I know some of you are really interested in politics. Back in the Cold War, right? The U.S. tried to influence other country by bringing its military, okay, and occupy many area during the Cold War, okay, and influence that country. And they say that if that country is influenced by a capitalism, so the surrounding country must be influenced by capitalism, and if it is influenced by capitalism, so it will be influenced by American politics. Okay, okay. So if one country is falling, if one country is not following communism, the other country will not follow communism. That's what I mean. That's what the domino effect in politics. But what is domino effect in mathematics? In mathematics, the domino effect, it means that if the first statement is true, okay, it will make the second statement true. And the second statement is true, okay, that lead to the third statement, and so on and so on. And finally, so many statements will be true. Okay, and if it's so many statements is true, we can say that, we can say what? We can say that that statement is always true, no matter what. Okay, so the mathematical induction said that let m be an integer and let s of m plus 1, okay, so it's the second statement, s of m plus 2, and so on, be statement with property, okay. The first property is s of m is a true statement. Okay. S of m is a true statement. The second property is if s of k is true statement, then s of k plus 1 is also true. Okay. K is greater or equal to a. Okay. If we have these two properties here, we can conclude that then each of the statement Sm, Sm plus 1, Sm plus 2, and so on is true. That's what the mathematical induction is. Yeah. It's this domino effect. Okay. It's nothing but domino effect. If one fall, if one domino is full, the other domino will be full. Will be falling, and at the end, all domino will be falling. Okay, so at the end, all the statement will be true, no matter what. Okay, so how are we gonna prove this? How are we gonna prove this? I'm gonna use this theorem here to prove the first principle of mathematical induction. I don't know, some of you maybe heard that the first principle of mathematical induction, it can be called the weak principle of the weak induction. The second principle, we call it the strong induction. Okay, but all three principles here were ordering principle. The first principle of mathematical induction, the second one is equivalent to each other. It means that we can derive one principle from the other principle and vice versa. Okay, so how are we going to prove this principle? Or using the theorem I just proved, using the theorem right here. Okay. So this is what we need to get, right? We need to show that all the statement will be true. And we try to use the theorem here. And try to use the theorem. I'm gonna just leave over here. Okay. I know that z sub m is always true, right? Z sub m is the set of all the parts of the integer that is greater than m. This is always true according to the well-ordered representation. This is true already. So just think about it. If we call a set and that set contain, okay, that set contain of this statement. Okay, that says it contain of the number, and then the number, I'm sorry, that says contain a number, and that number here it satisfy the condition that the statement is true. Okay, and we show that that set is equivalent, is equal to z sub m, and z sub m is true already. Then we can say that the set of number that is s sub m is true. Okay, the set of number that satisfy all the statement here is true. Okay, will imply all the statement here is true. The statement here is true. Okay, so the first step we have to do is we have to call S is a set of integer. I call it integer I, for example. And this integer I here is greater or equal to m. And the condition for this set is S of I is a true statement. It's a set of integer, but that integer must satisfy the condition that S of sub of that integer must be true statement. So we know if we can prove that this set over here is true, okay, is true, then all of them over here will be true, right? All the statement over here will be true. And in order to do that, we need to show that S is equal to z sub m. All right, so how are we gonna do that? So of course we're gonna use that what they've given us, right? So we know that S of m is a true statement. S of m is a true statement. And S of m is a true statement. Okay, then of course m must be belong to S, right? M must be a member of S. M must be an integer of this set of integers. Okay? That is what we get first. Then what next? What we're gonna do next? What we're gonna do so that we can conclude that S over here equal to z sub m. If K belong to S, so think about it. If K belong to S, then of course S of K is a true statement, right? Okay, belongs to S, and okay, it must be a true statement. Okay, but if S of K is a true statement, okay, if S of K is a true statement, and we have what? We have, if S of K is a true statement, then S of K plus 1 is also a true statement. And if S of K plus 1 is also a true statement, then K plus 1 must be a number, it must be the integer of the set S, right? And K plus 1 must be the integer of set S, right? And if K is an integer of set S, okay, and K plus 1, oh, I'm sorry. According to the theorem, what? If K is an integer of set S, and K plus 1 is also the integer of set S, okay, then what? Okay, then what? Then S, and because of what? And because S is a subset Okay, S is a subset of, since S is a subset of Z sub M, right? Okay, this S is a subset of Z sub M because this set is an integer that greater than N and satisfy this statement and satisfy this, right? Then of course S must be a subset of Z sub M, and S over here satisfy, okay, and S over here satisfy the condition here, satisfy the theorem, okay. So what? So we can conclude that. S is equal to Z sub M, right? Think about it. Let's start from the beginning, okay? Let's start from the beginning. I know this is kind of a little bit crazy, but if you think deeply, that this is okay. It's not really that bad, okay? We want to prove that all the statement over here is true. That is what we want. We want to show it. And in order to show all the statement over here is true, we're gonna call a set of integer. And that integer is greater than n, and satisfy that S of I, we say I over here, and satisfy that S of I is a true statement. If we can show that this set over here is equal to Z sub M, Z sub M is this, okay, equal to Z sub M, okay, then what? Then all the Si must be true, right? All the Si must be true, and I greater than must be true, right? So how we do that? We start with a set, okay, and we know that what is they given us? Sm is true already. If Sm is true, if M is true, then M must belong to S, right? Because we call this set over here, as long as satisfy this condition. So this is the condition right here. As long as satisfy the condition, then of course it belongs to S, right? And if K belong to S, okay, if K belong to S, okay, then if K belong to S, because over here K is greater than M. So if K greater than M, so if K belong to S, right? K belong to S, then S of K also true. And if S of K also true according to what they give us, if S of K also true, then S of K plus 1 also true. And if S of K S sub K plus 1 is true, then K plus 1 belong to S, right? So we have K belong to S and K plus 1 belong to S, right? Okay, and S is a subset of Z sub M. So according to the theorem, if K belong to S and K plus 1 also belong to S, okay, then of course S must be equal to Z sub M. Okay? S must be equal to Z sub M because we have K belong to S, okay, K belong to S, and K also belong to K plus 1 also belong to S, right? Okay, then of course S must be equal to Z sub M, and if S equal to Z sub M, then for I greater than or equal to M, Si is a true statement. I'm sorry. Then I is greater than M, S of I is a true statement. Okay, so then we finish it. Okay. All right. So in the second video, I think I'm gonna stop over here. But in the second video, I'm gonna prove the well ordering principle by the first principle of mathematical induction, because I already told you that they're all equivalent to each other. So it means that you can prove one principle by using the result of another principle. Then if I have time, I also proving the strong induction, the second principle of mathematical induction, using the first principle of mathematical induction. Okay. So I think I'm gonna stop the video over here. If you guys have any questions, just let me know. Uh, uh, I don't know is any other part that is not clear enough to you. If you think that's not clear enough to you, you can let me know also. Or you find out something that doesn't make sense, but please also let me know. Okay, then I'll see you next time. Bye bye.